Welcome to the multi-armed bandits world, and here we will see how to assign treatments adaptively. Why is that interesting? Because randomized controlled trials have been the gold standard for causal inference for a while now, but adaptive experiments allow for earning while learning. And there is a push to replace non-adaptive experiments with bandits. And that has been done in medicine, economics, political science, survey methods, research, education and psychology and other sciences. And it's an exploding literature. So also practitioners use heavily bandit algorithms. So for example, if you watch Netflix, you have been part of a bandit experiment perhaps. Also, if you surf Google, probably you have been part of a bandit algorithm. So why is a bandit useful? Because it can improve outcomes and it can also improve policies learned at the end of the trial. We will take a look at some popular algorithms, that is epsilon first, epsilon greedy, upper confidence bound, and the Thompson sampling algorithm. And the basic structure of multi-armed bandits is as follows. Imagine you're a researcher and you have to treat cancer patients. You have two drugs, A and B, but you don't know how these drugs perform, what the success rate is in terms of how many people will survive and how many people will die. So if people survive, your reward will be 1. If they die, your reward will be 0. So you could code this like in the binary case. Now the question is, which arm does perform better, and also which arm should I play? And you would like to know that already during the experiment, because in traditional randomized controlled trials, you only after a lot of people died know which one worked better. And adaptive experiments give you the possibility to already, while you're doing the experiment, use the arm that works better more often. Now, to put multi-armed bandits into the reinforcement learning framework, you can adapt the cycle of reinforcement learning by putting the bandit algorithm where the agent is. So that's the agent now, and it selects an arm, interacts with the environment, gets a reward, and then this circle goes on as usual. So multi-armed bandits are a sequential decision-making problem that is seemingly simple and simple to write down, but difficult to solve, to find the optimal arms. That's why we have the bandit algorithms. So the agent chooses among those arms repeatedly, and each arm has an unknown success rate, an unknown reward. And the objective is to maximize the total rewards. So we need to first learn which arm works better and which one does not. And when we know that, we can exploit that and earn. But how to balance exploration and exploitation? Well, we need to understand algorithms for that. Bandit algorithms, how can we actually judge which algorithm works well and which one not? To understand this, we need to define the exploration-exploitation dilemma. And basically, for each action, for each arm, there is an expected reward that we denote by QA. And we estimate that in our experiment for each time step that we have there. And if we always take the best arm, then we are greedy. That's the greedy strategy. Then we are not exploring. We are always just taking the best arm, and we have no possibility to learn about the performance of the other arms. So we need to kind of also explore a little bit. And but if we do explore, then we incur a loss. So this loss is known as regret. Think of the cancer patients. If they die, then that's a regret. So we calculate the optimal value of having chosen always the best arm and denote that by R star. So that's the action value of the best arm. And Basically, that's the maximum of all the arms that we take. And so the loss per time step per trial is then the expectation of this best action value minus the action value that we have actually in our experiment. So the R star is something that is hypothetical a little bit, but we will see how to do that in practice as well. And the total regret is just the sum of all the losses that we incurred over time until the end of the experiment, which is capital T. Now, one property of these multi-arm bandits is that if you look at the regrets per round, it's equivalent as if you look at them over each arm. And to understand that, let's take a look at this example where we check out when have we played arm A. Out of the 16 trials that we have done so far, we have 10 times used arm A, and 6 times, the bluish ones, we have a success. So the success rate is 6/10, which is 60% for arm A. For arm B, we have played it 6 times, and we have only 1 success. So 1/6 is around a little bit less than 70%, which is our success rate for arm B. Now, clearly, arm A performed better, so the optimal arm in this case is arm A so far. And if we want to calculate the regret, we can use the per round regrets. So we calculate for each round what would have happened if we had played the better arm, the best arm actually. And so because when we played arm A, it's already the best arm, we have a loss of 0. But if we have played arm B, then we could have played arm A, and we would have a success rate of 60%. In reality, we have only 17%, so the difference is 0.433. So that's gonna be our loss. And we played 6 times the suboptimal arm, so we have a total loss of 6 times 0.4, which is 2.6. Now, if we take all the arms and sum the regrets up over the arms, then we will see that this is going to turn out to be the same number, 2.6. So the difference here is that we take the regret for each arm and multiply it with the number of times we play that arm. So here it's 10 times we played arm A with 0 regrets, so that's 0, plus 6 times arm B, and that's again the 2.6. Now this holds more general and is going to turn out to be useful. And here you see that we can rewrite the formula that we have seen before for the loss, just in terms of the sum over the arms instead of the sum over the periods. And in this rewritten formula, we see that the expected number of times we play each arms is decisive for how much regret we have. Another property of the multi-arm bandits is that we can actually, instead of storing all the rewards, we can check out arm A, for example, and sum them up, form a running sum up to n-1, and then count how often have you played arm A, that's 10 times. And then we can calculate our expected reward. So for example, in round number 3, we have 1 success, 2 trials is 50% success rate. In round number 15, we have 6 trials, 6 successes, 10 trials, that's 60% success rate. We can also move that down, so shift that in time to just have stored that number, because we want to actually get to the Q of n just by taking track of the Q of n in the previous period. That's the idea. And why? Because we then can have an incremental updating rule, which is a learning rule. And here is the incremental updating rule. Q of n is just the average of the returns up to n-1. So if we move in the next period, we get a reward Rn. And so in Qn plus 1, our estimate for the expected return in n plus 1 will be the average of all the rewards up to n. And we can decompose this into the reward that we just observed in Rn, in period n, plus the ones that we already got. And now if you go back to the Qn formula, then we can multiply both sides by n minus 1. And then we see the right-hand side turns out to be the same sum that we have in the Qn plus 1 formula. And we plug it in. Then we have 1 over n times Rn plus n minus 1 times the Qn, with the correct parenthesis, of course. And if you multiply that out, we have the old value of Q plus 1 over n times the new reward that we just got minus the old value of the Q. And if we calculate it out, we get the new value. And that's an incremental updating rule. That means a new estimate is based on the old estimate plus a step size, 1 over n here, times the error. And that's a learning rule, sorry. And that's really cool because it's telling how you can keep track of your estimate in the future just based on the past estimate and your signal. So how does this work in this example? Well, we select arm A, we store all the Qs in the previous period, we use the updating rule, and we get the new Qs. Now we want to have sublinear regret for multi-armed bandits so that the average regret vanishes as the number of rounds increases. So basically, when we have explored enough, we want to stop learning and just exploit. When we don't do that, then we have linear regret. So that means we always learn, but we also always have regret. So here's an overview of algorithms. The greedy algorithm, the epsilon first, the epsilon greedy, they all have linear regret, which is, well, not really good because we will always learn. If we use the version of epsilon greedy that is decaying, that has a decaying epsilon, then we will end up with logarithmic regret, which is great, which is, we cannot do better actually. People have shown that logarithmic regret is the best. UCB, Thompson sampling, they also have a logarithmic regret. And here are some references, but first let's take a look at Bandits in practice before we wrap up the session. So Netflix is one example where you have these multi-armed bandits in practice at work. Here the actions are to choose among k images to display a movie for the users. Now the ground truth rewards are unknown. We don't know how many people will click on the image and watch the movie, so we need to estimate that. And we can even use some contexts in more complicated bandit models. For example, the user's history or preferences for specific types of movies. And here you see image A and image B. And if you randomly show these kind of images, well, then you get a take fraction, which is the measure of success. But if you use then bandits, or even contextual bandits, you get a higher take fraction. So here are some more references. Takeaways: multi-armed bandits are adaptive sequential decision-making models. Under uncertainty, the core trade-off is exploration versus exploitation. And the objective is to maximize total reward or minimize regret. And the key algorithms are epsilon first, epsilon greedy, UCB, and Thompson sampling. Thanks for watching and see you in the next video.